Well, as we promised a little bit earlier, there's a slight change in the order of the program, and so when I heard of some of the issues earlier in the week, I volunteered to Zach to say, if Jeff doesn't make it, my boys will be ready. And so at 9:20 this morning, we found out we really ought to be ready. And then after Nick's exciting presentation and the technology, the guys have absolute confidence the system's going to work flawlessly, and as they work through it. The other thing that happened is the other half of the presenters had to make a trip to a room outside this room and has not yet quite returned, so I'm stalling a little bit of time. But basically at DePauw, talking about the education, which is what we do all the time too, as Nick mentioned, one of our programs we have at DePauw involves what's called the Science Research Fellows. Those are students who are invited to be in the program. They're guaranteed a summer research experience, which is what Mark and Richard are doing right now. They've spent a semester during the year in a small group doing research with another professor in some fashion. We like them to always have internship opportunities if possible. Actually, Richard's going to be not interning this fall, but he's decided he likes DePauw so much that he's going to study off campus in the fall at Oxford. And so Richard will be there. And Mark is here now as well. So this is a talk that they've given in various locations. We went to the Academic High Altitude Balloon Conference last month at Taylor, and they talked a little bit about some of this. So they kind of tried to modify it, not spend as much time on putting them up and getting them down, but talk a little more about the science that we're doing with it. So I don't remember, guys, who goes first? Richard goes first? Okay. Richard and Mark.
Okay, hello, everyone. My name is Richard Ma. I'm from Beijing, China. I'm a physics major junior at DePauw University in Greencastle, Indiana, not the Chicago one. We are DePauw. And that's Mark Tully. He's going to be a pre-engineer sophomore at DePauw. So today we're going to talk about our base project at DePauw University with Professor Brooks.
Hi, Mark. Well, BASE, which is created at DePauw, stands for Balloon Assisted Stratospheric Experiments. We fly helium balloons, and our systems were provided by Stratastar in Upland.
So our project this summer mainly deals with cosmic radiation. We aim to measure cosmic activity in the atmosphere by flying those Geiger counters. Here's a picture of the Geiger counters.
Well, I guess we can just give a brief background on cosmic radiation. I think someone's having a presentation later. We're mainly focused with gamma rays, beta particles, and like the electrons and ions that they create when they hit the atmosphere. And go next, Geiger. This is just a sample picture of a particle hitting a particle in the atmosphere and creating the electrons or photons that break off and hit our atmosphere. And what we've seen is basically two factors of radiation, the density of air molecules and intensity of the radiation. As we know, density of air is less as we get up, and intensity also increases as you get higher. And what we've seen is an increase in counts from our Geiger counters as we get higher, obviously. And although there's less particles to hit because the density is less in the air, since the intensity is much greater, we get what we're going to describe in detail as our showering effect. That gives us more counts and increase then decrease at a critical altitude, which we'll explain more.
So lead shielding is a commonly used form of protection from radiation, and we adopt this method of shield to see how the lead shield would affect our counts, and the result is pretty interesting that we're going to talk about later. These are the equipment we usually fly, as you may be familiar with. The main thing we are dealing with is the Geiger counter, and sometimes we fly to sensors and camera for fun. This is a picture of a gyro counter, actually the tube. The tube consists of mainly two parts. One part is the wall. Well, it's a tube, so it's wall, and there's a pin in it, and there's about 100 voltage difference between the wall and the pin, and the chamber is filled with inner gas. So when there's a particle penetrate the tube, it will generate a spark inside the tube, and the circuit outside the tube connected to the tube will register this current and make a count. This is basically how a gyro counter works. And we're using a RM60 gyro counter, as you can see in the folder. There's a sheet about it, and all the gyro counters are attached to a basic STEM microprocessor, and we are using a 555 timer circuit to process the raw information into readable data to computers. The counters are programmed to record the total counts for every consecutive minute or 30 seconds, which is determined, like, we can design whatever time slot for that, up to 16 hours. And we use different kind of shield to conduct our experiment. These pictures are the two type of shield we've been using this summer, and we'll talk about it later in detail.
All right, so we started in the spring of last year with Professor Brooks, and we're continuing in the summer. And we've done 2 flights in the spring, 41 and 42. And this is just graphs. You'll see throughout basically all of our graphs a consistent kind of M-shaped curve with the different counters that we use. We typically like to fly 3 counters, but since we've broken a couple, we've had to fly 2 a few times. Also, you'll see, which we'll discuss in our analysis, is that we have different shielding. This one, we're only doing partial shielding around the box instead of the whole box. And with all of them, you'll see as you get higher up, the shielded ones with the heaviest amount of shield give us the most counts compared to the non-shielding. And these are just our spring flights, which the most shielded counts most, the M shape. And then starting our summer, there's only 2. And then these last ones are our new 30-second counts, in which we get counts for 30 seconds for 8 hours, and then we just times it by 2 to get our counts per minute. Yeah, well. All right, so here's kind of our analysis. And as I said, we see an M shape, and we briefly mentioned what we said was a critical altitude, how as we reach a critical altitude, our counts lower. And I don't know if this has a pointer or not, but no. All right, so we kind of labeled it the critical altitudes in the burst. As you can see, our counts keep on increasing until we hit our critical altitude, which will tell you what our data shows. And then they start to decrease until burst. And then obviously, since you burst, you fall back down through the critical altitude, and then they continue to decrease. And we saw this throughout all of them. And as we've done research, the phosphor maximum, which won the Nobel Prize, in which he also discovered this critical altitude, which we confirmed throughout our data. And then here's just a different way of showing it counts per minute compared to altitude, as the counts keep increasing until a certain altitude, then they start decreasing. And then here's our critical altitude for the 6 flights that we've done. We see that our average is around just over 67,000 feet, plus or minus 2,000 feet, which is 1 standard deviation, and about 83% of our data is in this range. And we listed our flight data through calendar days because we also read that there might be like a seasonal variation with the critical altitude, but as you can see, about 83% holds true. So we didn't really see, besides a couple outliers, that there's a seasonal variation. Yeah, we didn't fly all 50 times. Also, just, I don't want to say for fun, but our professor kind of led us to look into this, what we call a crossover altitude, in which the shielding, which I said provides more counts than non-shielding, which Richard will talk about next. Kind of just where these altitudes switch and which the non-shielding counts less. And for these are just 3 flights we've given from about 30 to 40,000 feet. We see this crossover altitude, which we've labeled, and kind of just what we've noticed is that it's where the commercial airline flights take place. So I guess we're going to have to do a little more research into why, but maybe since there's more metal there, provides more counts, which Richard will tell right now.
So another thing we've seen from our data is that the shielded counters give us higher counts than the unshielded one, which is very surprising because the initial purpose of the lead shield is to see how it decreases the counts, but actually it increases counts. So in the spring, we've seen this happening twice, and we think there might be something that leads to these higher counts of the shielded counters. So we continue to design experiments to investigate why this is happening. And here are the summary of the data we've done on ground. And for the flights we've done during the spring, which are 41 and 42, we use the box-shaped shield, which is all wrapped around the Geiger counters. But for this ground test, we just use the tube shield one. We open the Geiger counter and pull out the tube and just wrap the lid around the tube. So it's we can achieve a thicker thickness with a less mass of lid. Here is a summary. The general information, the general result is pretty expectable because with thicker shield we get less counts. But the interesting thing is here that with 2.6 millimeter thickness of lead shield, the counts actually higher than the 1.6 millimeter shield. The only difference between these two shields is that the 1.6 millimeter shield is wrapped tightly around the tube, while the 2.7 millimeter one has a bigger diameter. So we might think that the geometry of the shield may affect the counts. By the way, all these runs last 16 hours. So even though these two thickness of shield just had one run, but we believe that the data is pretty consistent. These are the two types of shield I talked about. And we've seen that the geometry of the tube may affect the counts, so we continue to design our experiment that we use the different type of shield with of about the same thickness. One is 2.9 and another is 2.7. And the result is consistent from our previous result that the box counts more than the tube, even though the total counts decreased, but the box gives more counts than the tube with about the same thickness. And our data from here's some drawings that demonstrate what we believe was happening there. this is like all the red lines are shows the path of energetic particles. As you can see, there are some that go through the tube and some others like miss the tube. With the shield there, you can see some of the particles still can go through the shield because they are so energetic that they just penetrate the lid. And some of them are absorbed by the lid because they are not energetic enough. And some of them may hit the lid and create a shower there, which means such shower may be ionizing radiations that electrons come out of a lead molecule, or just pair production. And sometimes previously we believed that the Geiger counters can register multiple numbers during for a single event. But after we read the manual, it says there's a quenching time of microseconds, 90. So we believe it can register multiple counts for one event. But the shield probably makes the tube bigger. So for some particles that might miss the tube, may actually create a shower that some of the secondary particles go through the tube. So in this way, we get higher counts. And we can see in the low energy case, a lot of particles are absorbed by the shield, and some of them create a shower there. The total effect may be a lower count. When we are high in the air, the particles are so energetic that there might be more showering there, so we get more counts. And this drawing, we want to show that with a bigger case, some of the particles that will miss the smaller shield will hit the bigger shield and create a shower, where the secondary particles can go through the tube. So we believe that the enclosed volume of the shield may also affect the counts. And the bigger the volume is, the more counts we got, which we have seen from our experiment. And the data from our flight 45 proved our hypothesis that the box shielded one counts more than the tube shielded one, and the numbers are all normalized. This is from 42, and those shields are all box shielded. So even though the thicker one is 2 millimeters thicker than the 2.31, but in the volume wise, it's not. The volume is about the same. So we can conclude that with the same enclosed volume, the thicker the lid shield, the more counts we can get.
Okay, to wrap it up with some conclusions that we've seen, that the number of energetic particles increases as altitude increases until it hits our critical altitude, and then the counts start to decrease. Lead shield of a given thickness can only provide a protection from energetic particles up to a particular energy, as we saw with compared to 1.2 or 1.6 to 2.6 thickness. If the particles are too energetic, there exists a showering effect, which then increases the number of energetic particles. And then lastly, the enclosed volume and the shield thickness both affect counts. With the same shield thickness, more volume enclosed by the shield leads to more counts. With the same enclosed volume, the thicker shield leads to less counts on ground, but higher at high altitudes. And then further work, just continue to run ground tests and high altitude tests, and then hopefully we receive our floating valve here, which we can use tomorrow, and then possibly use hydrogen, but we're not sure yet. So that's all, and